One of the properties is reversal law of inverses. If A, B are any two non-singular matrices of the same order, then A into B, that is represented as AB, is also non-singular, and AB the whole inverse will be is equal to B inverse multiplied by A inverse. Let us find the proof. Since A and B are non-singular, determinants are not equal to 0. That is, determinant of A and determinant of B are not equal to 0. Right? So, we know that determinant of AB, A into B, equals to determinant of A into determinant of B from one of the previous properties. Determinant of A is not equal to 0 and determinant of B not equal to 0 implies, what it implies? Determinant of A into determinant of B is not equal to 0, which also implies determinant of A, B is not equal to 0. This is the important line. Hence, AB is also non-singular. The reason is, we found if AB is a non-singular one in the part of the definition, okay, to non-singular matrix. So AB is invertible. If they are non-singular, then they are invertible. That is, we can find inverse for that. AB into B inverse A inverse equal to A into B inverse. This is by the commutative property of the matrix into A inverse. You can see this one, okay. This can be represented as B into B inverses is identity. That is, 1 in matrix terms is called identity matrix. So A into identity matrix into A inverse, which is equal to A into A inverse, which is once again equal to an identity matrix. Similarly, we can show that B inverse A inverse into AB equal to identity. Same method, okay. Having B inverse and then clubbing together the central piece like A inverse and A, and since A and A inverse is identity, B inverse into B is also identity. Hence, this is equivalent to identity matrix, okay. Therefore, AB into B inverse A inverse equals B inverse A inverse into AB, which is equivalent to identity matrix. Therefore, B inverse A inverse is the inverse of AB, okay, because AB into B inverse A inverse equal to B inverse A inverse into AB, which results in identity matrix. Hence, B inverse A inverse is the inverse of AB. Therefore, AB inverse equal to 1, B inverse A inverse. Next one, we take the reversal law for transposes without proof. Okay, if A and B are matrices conformable to multiplication, then AB transpose is equal to B transpose A transpose. For any non-singular matrix A, inverse of A transpose equal to A inverse the whole transpose. This is the law. Okay, let us prove it. We know that A into A inverse is identity, that is A inverse into A. Taking transpose on both sides of A into A inverse equal to I, we get A into A inverse transpose, that is equal to I transpose. Okay, by reversal law for transposes, we get A inverse transpose A transpose. This becomes A inverse transpose and A transpose, that is equal to identity matrix when transpose is equal to identity. Okay. Similarly, by taking transposes on both sides of A inverse and A equal to identity, we have A transpose, A inverse transpose equal to I. Okay. From 1 and 2, this one and this one, right? A inverse of whole transpose into A transpose equal to A transpose into A inverse whole transpose, which is equivalent to the identity matrix. Do you remember how we came across that? We are substituting that here. Okay. Hence, we come to the conclusion A inverse transpose is the inverse of A transpose. That is, A transpose the whole inverse equal to A inverse the whole transpose. Okay? Bye. Thanks.